Before a wooden ship can touch the ocean, it begins deep in the forest. Welcome back to RaWMachines, where raw materials are pushed to their limits and transformed into engineering masterpieces. Today we follow the entire journey, from massive trees harvested in dangerous conditions, to precision-cut timber inside a working sawmill, and finally into handcrafted vessels built to endure the sea. Every cut matters, every joint carries risk. One mistake, and the entire process can fall apart. Let's begin. Everything begins in the old-growth forests of the Pacific Northwest. Here, Douglas fir, hemlock, and cedar are the dominant species. Their massive trunks are wide enough to build ships, bridges, or even entire towns. Naturally, given such colossal dimensions, harvesting them is never a simple task. The foresters rely on a time-honored technique called springboarding. They drive planks into the tree trunk to create a standing platform nearly 2 meters high, just enough to bypass the flared base and twisted grain, which are prone to splitting and pose a high risk of accidents. As the saw blade bites into the timber, every movement unfolds like a precise geometric equation. First is the face cut, consisting of 2 incisions that create an opening angle of 70 degrees to 90 degrees. This dictates the exact direction in which the tree will fall. Next is the back cut on the opposite side. The craftsman meticulously preserves a thin layer of wood, the hinge, acting as a control line to guide the tree's descent. Finally, the wedges are driven in. Small yet backed by immense experience, they keep the kerf open to prevent the saw from binding and provide the final, precise adjustment to the fall. Once the giants fall, they are bucked into logs and loaded onto specialized heavy-duty trucks. These vehicles are engineered to withstand colossal stress, with each truck capable of hauling between 25 and 30 tons of timber. Behind the wheel are seasoned veterans of the transport industry. They understand the nuances of every incline and every sharp curve, precisely when to downshift, when to maintain throttle, and how to manage the brakes to keep the massive cargo secure. Leaving the forest behind, our journey continues to the Hull Oaks lumber mill. This is the largest and last steam-powered sawmill in the United States, a place where these massive trunks are tamed by the raw power of steam, a capability that modern high-speed sawmills can no longer match. Upon arrival at the mill, the timber undergoes its first critical stage, debarking. While this process may appear straightforward, it is mathematically essential. The seemingly harmless bark can harbor soil, rocks, or grit, debris abrasive enough to devastate a saw blade. In a high-speed operational environment, such a risk doesn't just drive up blade replacement costs. It creates a lethal projectile hazard for workers throughout the facility. Next, the timber advances to the heart of the entire assembly line, the place where the true transformation begins. Within the vast expanse of the mill, the carriage emerges like a mechanical titan. Sliding along its steel rails, it grips the log with heavy iron, dogs, thrusting it directly into the path of the razor-sharp saw blade. Naturally, the machinery is nothing without the head sawyer. They are the soul of this operation. With keen eyes and decades of experience, the sawyer reads the timber, analyzing every grain, knot, and twist to visualize the internal structure hidden within. Immediately, a critical decision must be made. The opening face, the very first cut, is the pivotal move to produce the largest and most pristine planks. The right call results in a flawless structural beam. A single miscalculation, however, can turn tons of premium wood into scrap. The carriage retracts, the log is flipped, and the cycle repeats. Piece by piece, the log is squared and whittled down, its hidden value finally revealed. After the initial cuts, the planks still bear irregular, waney edges and a raw surface. The edger takes over from here, delicately shearing away the excess to leave behind perfectly straight, razor-sharp lines. Not even the discarded offcuts go to waste. They are pulverized into chips to fuel the paper industry and biomass energy sectors. Next, the lumber advances to the trimmer. This system consists of multiple saw blades spaced exactly 2 feet apart, which drop into action only when needed to shear the wood into standard commercial lengths. Any planks that fail to meet specifications are immediately diverted for reprocessing. This rigorous quality control ensures that not a single defective product ever leaves the assembly line. The arduous path is far from over. To prevent warping and cracking, an automated system categorizes and stacks the planks, inserting small wooden stickers to create critical gaps for air circulation. Following this, the entire stack of lumber is moved into an industrial kiln. This is a sophisticated scientific process where the wood's moisture content is reduced to approximately 10 to 15%. Only once it reaches this stable state can the timber maintain its structural integrity and long-term quality. Finally, after everything, the lumber leaves the kiln and enters the planer mill. Here, high-speed blades shave all 4 sides simultaneously, yielding a smooth, polished finish and precise dimensions, transforming raw timber into a finished commercial product. Now, the lumber is ready for its new journey, headed to construction sites, furniture workshops, and factories across the United States. And one of those destinations is the Drake and Harald Hårfagre Shipyard in Haugesund, Norway. Their goal, to build the largest Viking longship of the modern era. While the ancient Vikings built ships based on oral tradition, today's engineering team must begin with detailed technical blueprints. However, these drawings are constantly adjusted right on the shipyard floor to adapt to the unique natural characteristics of each oak timber block. The process begins with the keel, which serves as the foundation for the entire structure. From there, the initial molds for the bow and stern gradually take shape. Craftsmen like Ola, Gunnar, and Orild work with extreme care, adjusting every plank angle, every curve, and critical details like the hood ends, the decisive factor in the ship's seaworthiness. Unlike modern vessels, Viking ships are built using the clinker technique, where the planks are overlapped before the internal frames are fitted. This is a distinct approach where the builder does not force the material into a design, but rather lets the material itself dictate the form. Once the initial frame is defined, the planking process begins. Iron nails are driven from the outside through the overlapping planks. On the inside, a small washer secures the nail head before the excess is clipped and peened over. Each joint requires dozens of hammer strikes, creating the characteristic clink sound, which is also the etymological root of the clinker technique. Eric and his colleagues carefully install the next strake. The plank is naturally bent along the hull, held in place by wooden clamps before holes are drilled and rivets are set. Every maneuver requires high precision, as even a minor deviation can compromise the watertightness and durability of the entire structure. As the 8th strake is finished and the 9th begins, the hull gradually rises. From scattered planks, a resilient shell is forming, quietly yet full of life. Once the shell is sufficiently stable, the lower frame's floors begin to be installed. Each frame is steam bent and refined to fit snugly against every plank, ensuring a smooth contact surface and even load distribution. If done incorrectly, even a small point of tension could create a weakness when the ship encounters heavy seas. Lars and Stefan focus on the bilge stringers, the primary load-bearing area of the hull. Meanwhile, more strakes are added, raising the gunnels and completing the overall shape. Inside, longitudinal beams called stringers begin to appear, acting as reinforcement to help the hull withstand longitudinal pressure. At the bow, the work becomes more complex. The planks converge at a narrow point, creating the characteristic hood ends. This area requires near absolute precision, as it directly affects wave cutting ability and durability in rough waters. Simultaneously, Ola prepares the stern post while Arne tests the vertical stanchions. These components must fit perfectly with the hull, stringers, and cross beams, creating a tightly linked yet flexible network. As the framing system and plank layers become clearly defined, the upper stringers are installed. These beams are not a single solid piece, but are joined from two sections using a scarf joint. This type of joint extends the material while maintaining strength and distributing force evenly along the hull. Once in place, they help absorb and spread pressure from the crossbeams, making the entire structure more stable. The fastening process is slow and precise. Clamps hold the timber tight to the hull before they are secured with wooden pegs, tree nails, and wedges. At the bow, a symbolic task is underway. From oak blocks, specifically roots with complex natural shapes, the craftsman begins to shape the dragon head. Boney uses modern tools for the initial sketch, but the carving process remains entirely manual. The dragon head is not created from a single block, but is assembled from several parts, gradually forming a symbol that is both fierce and majestic. This is more than a decoration. It is the soul of the ship, the entity that will guide it across the ocean. Once the hull is clearly shaped, the centerline stringer is installed. This beam is fitted into slots on the crossbeams, running the length of the ship as a balancing axis. It helps distribute force evenly, keeping the hull stable under the impact of waves and cargo loads. Though nearly invisible from the outside, the centerline stringer is the silent element that keeps the entire ship upright in the middle of the ocean. Pater applies tar to a new plank. Over the tar layer, he lays a strand of hemp. This fiber acts as a sealant between the strakes. The planks are then brought together so that they overlap perfectly. At the bow, the longitudinal beams are installed. These beams are linked using mortise and tenon joints, fitting together precisely without the need for excessive metal. Combined, they create a tight bond that makes the bow rigid enough to take a beating, yet maintains the necessary flexibility. John takes charge of crafting the bow's stanchions, the area under the most pressure. 6 stanchions extend upward, not only increasing rigidity, but also serving as bits for securing ropes when docking. After more than 20 months of continuous labor, the ship nears completion. The freeboard, the part of the hull above the waterline, is raised to its maximum height, finalizing the ship's ultimate silhouette. About 10 craftsmen, through patience and traditional skill, have come together to recreate a technique that has existed for centuries. It is not just assembly, it is the restoration of a legacy, where every detail bears the mark of precious history. Next, we head to the Jarrett Bay Construction Center, where the Hull 64 project stands as a definitive icon of distinct maritime philosophy. This isn't just about assembling a vessel. It is a conquest of the boundaries of material science and hydrodynamics. The foundation begins with the structural backbone known as the strong back. In an era dominated by automation, Jarrett Bay continues to preserve the cold-molded boat-building tradition unique to the Carolina coast. Structural strength is achieved through the integration of 3 interwoven layers of marine plywood, reinforced with high-strength fiberglass. The precision in shaping the frames and forming the hull is critical, determining how the vessel cuts through waves, maintains stability, and endures the harsh conditions of the open ocean. The technical peak of Hull 64 lies in its propulsion system. Establishing the shaft alignment demands absolute accuracy, where the positioning of the propeller, struts, and engine output must reach perfect balance. Clearances and strut angles are tightly controlled using specialized measuring equipment, optimizing water flow dynamics and overall energy efficiency. Beyond mechanical specifications, the project demonstrates advanced logistics management and master-level craftsmanship. From installing the molded tunnel to achieving a mirror-like finish in the final coating, every stage adheres to the most demanding standards in modern shipbuilding. Yet, every advancement is rooted in the foundation, where the art of traditional shipbuilding has been forged through time. At this traditional shipyard, an icon of classic maritime engineering is being revived, the Mayflower 14-foot clinker dinghy. This is not merely the construction of a boat, it is a test of mechanical precision within a purely handcrafted process. The shipwright begins with the lofting process, scaling the blueprints up to a 1-to-1 full-size layout directly on the workshop floor. Every curve of the keel and the hull's lines are calculated with absolute accuracy to erect the system of molds. The keel is securely fixed onto the building berth. Next comes the fabrication of the stem and the transom. The shipwright uses robust blocks of oak, meticulously shaped to create perfect bevels. The joint between the stem and the keel requires expert joinery and specialized marine adhesives, creating a unified structure capable of withstanding immense compressive force from the water. The real challenge begins with the clinker planking process. Each wooden plank is cut into a complex geometric shape so that, when bent, it fits snugly against the hull's curvature. The hallmark of the clinker technique is that each subsequent plank overlaps the edge of the previous one by a small margin. The craftsman utilizes dozens of C-clamps to hold the planks in position before pre-drilling and driving copper nails. Each copper nail is secured by being peened over a rove, creating a durable mechanical bond that still allows the wood room to breathe as it expands in the water. The real challenge begins with the clinker planking process. Each wooden plank is cut into a complex geometric shape so that, when bent, it fits snugly against the hull's curvature. The hallmark of the clinker technique is that each subsequent plank overlaps the edge of the previous one by a small margin. The craftsman utilizes dozens of C-clamps to hold the planks in position before pre-drilling and driving copper nails. Each copper nail is secured by being peened over a rove, creating a durable mechanical bond that still allows the wood room to breathe as it expands in the water. Once the outer shell is complete, the boat is lifted from the molds and turned over. At this stage, work on the interior begins. The ribs, made of flexible timber, are softened using hot steam and then bent directly into the hull. They are riveted through the planking to increase lateral rigidity. Following this is the installation of the gunnels and the thwarts, transforming the hollow hull into a sturdy and functional structure. The stage requiring the most patience is surface treatment. Every square inch of wood is sanded from the coarse to fine to eliminate all imperfections. The initial coats of preservative oil penetrate deep into the grain, followed by at least 5 to 7 coats of premium varnish. Between each coat, the boat is lightly sanded again. The result is a mirror-like finish that accentuates the golden glow of the natural wood grain, while creating an absolute protective barrier against UV rays and salt water. The final steps involve installing the mast, the rudder, and polished brass fittings. Each rigging line is threaded through its blocks, and mooring hardware is bolted into strategic positions. The Mayflower 14-foot clinker dinghy now stands as a masterpiece, the culmination of hundreds of hours of labor and dedication. The vessel is more than just a means of transport. It is a living testament to the preservation of traditional maritime skills for future generations. At Fosen Folkehøgskole, Norway, a unique engineering process is underway to challenge the dominance of modern composites, the recreation of wooden boats using traditional Nordic methods. Instead of seeking perfectly straight trunks, they scout for specific sections of stems or roots with natural curvatures that match the contours of the bow and frames. This technique preserves continuous grain structures, creating mechanical strength that no modern steam bending method can rival. At the sawmill, the rugged logs begin to reveal their stunning grain patterns under the saw blade. Each plank is milled to a meticulously calculated thickness. Back at the woodworking bench, manual craftsmanship takes center stage. With razor-sharp axes and hand planes, the shipwright meticulously shapes the keel and the stem post. Precision at this stage is measured by the artisan's touch and traditional bevel gauges, ensuring the vessel's foundation is perfectly symmetrical. This is the soul of northern shipbuilding. Rather than joining edges flush, the planks are overlapped like fish scales in the clinker style. Every joint is manually pre-drilled, followed by the insertion of iron or copper nails. This stage requires absolute coordination between two people, one driving the nail from the outside, and another using a hand dolly to peen the washer, rove, tight on the inside. Thousands of rhythmic hammer strikes do more than just join wood. They create a hull structure that is both watertight and exceptionally resilient against the pressure of massive waves. Once the outer shell has taken shape, the team begins installing the internal framing system. Oak knees are carved to fit the hull's curvature with zero tolerance. They are secured with traditional wooden trunnels, tree nails, allowing for even load distribution along the hull. Next, the oars, thwarts, and mast are handcrafted from timber that is lightweight yet flexible. Every square inch of wood is sanded smooth and coated with linseed oil, making the vessel glow with a golden hue under the sun. The big day has arrived. Without the need for heavy machinery, the collective power of the team pushes the boat along wooden rollers toward the water's edge. As the hull touches the cool current, it officially becomes a living entity. The white sail is hoisted, and the boat glides gracefully yet sturdily across the fjord. This is more than a technical achievement. It is a brilliant continuation of a legendary maritime civilization through the hands of the next generation. Today, our woodsman faces a formidable challenge, taking down a western red cedar with a massive diameter of 4.3 meters. The first cut made is the directional notch. As the saw blade bites into the trunk, thick layers of seasoned wood are gradually revealed. This is a critical step, as it dictates the precise direction in which the tree will fall. Once the rough cut is complete, the woodsman takes an axe to meticulously clean every edge of the notch. This provides better control over the fall and minimizes unpredictable variables once the tree begins its descent. Moving to the opposite side, the woodsman begins the back cut. However, because the trunk is so immense, a standard saw blade cannot penetrate all the way through. To overcome this, he must carve a window into the trunk to feed the blade deeper, reaching the very core of the tree.
Best I can, so I guess I'll just have to get another tree and hit it and see if I can knock it over now.
Afterward, wedges and a sledgehammer are used to apply mechanical leverage, forcing the tree to lean without further sawing, while also preventing the risk of the saw blade becoming pinched. And then, the moment everyone has been waiting for arrives. The trunk begins to tilt, then crashes thunderously to the ground. As the dust settles, the colossal scale of the stump is finally revealed. The cross-section is smooth and flat, spanning over 4.3 meters. The woodsman walks across it as if standing on a small stage, completing a high-stakes mission with absolute precision and safety. Once the tree is down, the trunks are bucked into logs and loaded onto specialized heavy-duty trucks. The logging roads are unpaved. The trucks must crawl at an average speed of 15 to 20 kilometers per hour to prevent a rollover. On sections with gradients exceeding 12%, drivers must rely on pneumatic braking systems and full differential locks to maintain steering stability and traction. As the trucks approach the industrial zone, the forest gradually recedes. The landscape shifts, dense canopies and damp earth are replaced by steel fences, factories, and rows of smokestacks. This is where the logs will be reborn into a new form. Our destination is Sierra Pacific Industries, better known as SPI. Founded in 1949, this company is renowned not only for its massive output, but also for managing forests as a sustainable life cycle. Every log carries its own unique identity, marked, sorted, and logged into the system. Nothing here happens by chance. From dimensions and origin to quality grade, every variable is tracked throughout the entire journey. As soon as the logs leave the storage yard, they undergo the first stage of the processing line, debarking. While it may sound simple, this is a critical step that directly impacts the efficiency and quality of the subsequent sawing. The mill utilizes a ring debarker. A sensor system accurately measures the log's diameter, allowing hydraulic blades to automatically exert precise pressure, stripping away the bark in just a matter of seconds. The byproduct bark is then collected and ground down to be used as mulch or biomass fuel, a way for the tree itself to continue serving long after it has left the forest. The log then enters a large bandsaw system where the first critical cuts are made. The blade, over 15 meters long, moves at extremely high speed, powerful enough to split even the largest trunks. The operator does not stand next to the machine, but works from an enclosed control room, monitoring everything through screens. Here, each cut is carefully calculated to maximize yield and minimize waste.
So, be able to get an FOHC name out of this, or not really?
Not every log is perfectly straight. For curved logs, a specialized curve saw system comes into play. Sensors scan along the length of the log, detecting the natural curvature of the grain, and adjust the blade to follow that structure. The result is lumber that retains its strength while reducing material loss, a balance between technology and respect for the tree's natural form. After passing through the primary saws, the log is divided into several parts: the cant, a thick squared core used for further precision cutting, the flitches, rough boards with bark edges, which will be sent to edge trimming machines, chips and smaller fragments, directed to the grinding system for recycling. All of these continue along conveyor belts, moving into the edging and trimming line, where the true shape of the timber begins to emerge. At the edger, curved and uneven bark edges are stripped away, replaced by straight parallel sides, the essential standard for construction-grade lumber. The offcuts are never wasted. Instead, they are routed to a chipper to be processed into wood chips for the paper industry or biomass energy production. Next is the trimming stage, where the boards pass through a multi-saw system to be cut to standard lengths. At this point, each cut is no longer about shaping, but about finishing, standardizing the product to be market ready. The finished lumber then moves to the final grading line. While machinery plays a massive role, humans remain the decisive factor at this stage. Highly skilled graders inspect every single board, evaluating them against the rigorous standards of the American Lumber Standard Committee. They scan for knots, grain patterns, and even the smallest defects to determine the grade. This is where experience becomes irreplaceable, where a single glance can decide the market value of the entire board. The final stage, and perhaps the most delicate, is kiln drying. The boards are stacked into the kiln system, where every parameter, including temperature, humidity, and duration, is precisely adjusted via sensors and software tailored to each specific wood species. A drying cycle can last over 10 days, with countless measurements recorded continuously. Throughout this process, the wood is not only dried, but also stabilized, minimizing the risk of warping, cracking, or deformation. When complete, the wood takes on a light golden hue, the grain patterns become distinct, and the sound it makes when tapped becomes clearer and more resonant. This is the hallmark of completion, closing the circle of the timber's journey from the forest to the factory. When they leave the mill, they are not just industrial products, but a reflection of how Sierra Pacific Industries combines traditional woodcraft with modern technology to create materials that are both high quality and aligned with sustainable development, fully embodying the values of a new era. The journey inside the mill may have come to an end, but the story of wood does not stop there. In Cornwall, England, an extraordinary project is underway. An ambitious restoration of 18th century maritime heritage, the construction of the three-masted sailing ship, the Greyhound. This is not simply shipbuilding, it is an effort to reclaim the pinnacle of wooden shipbuilding craftsmanship once lost to time. The project officially commenced on March 1, 2011, in a small carpentry workshop in Millbrook, where the first handcrafted details were meticulously carved. By late July, as the timber components grew in scale, the entire crew and inventory were relocated to a larger facility in South Down to begin the primary assembly phase. As August arrived, the Southdown workshop was cleared to make way for the ship's most critical component, the backbone. With the aid of overhead shop cranes, each piece was lowered into position, the keel running along the bottom, the stem reaching forward, and the stern post set at the rear. Every alignment had to be near absolute in its precision. Even a minor deviation could compromise the ship's final lines and hydrodynamic performance. Once these components were secured, the vessel possessed its first clear foundational structure. Out of scattered materials, an organized framework began to emerge. Immediately following, the first ribs were erected. Each frame had been prepared in advance, but they only fulfilled their function once integrated into the keel. The work started from the midship, the widest section, and gradually spread toward the bow and stern. The frames were set in sequence, defining the width, depth, and overall silhouette of the vessel. While machinery assisted with the lifting, the accuracy still relied heavily on the artisan's skill. They didn't just assemble, they inspected and adjusted every detail to ensure a perfect mechanical fit. With the initial frame stabilized, the installation continued at a steady pace. New ribs were added, radiating outward from the center to complete the hull's structure. Each rib carries a unique geometry, with its curvature and height calculated to create the ship's signature lines. It is this collection of varied shapes that, when combined, forms a harmonious whole, where every small detail defines the collective beauty. As the height grew, scaffolding began to surround the hull, allowing the shipwrights to access and work on the upper reaches. Gradually, the skeletal frame transformed into a recognizable entity, still hollow, yet possessing the undeniable presence of a vessel taking shape. By October, as the final rib was slotted into place, the entire skeleton of the ship was officially complete. It was no longer a collection of individual parts, but a unified, coherent structure. However, this skeleton was not yet fully stable. Under the influence of gravity and the environment, the ribs could shift or twist. To counteract this, longitudinal battens were installed, running the length of the hull to keep the spacing between the ribs perfectly uniform. These battens maintained the precise fairing of the hull, a crucial factor for the ship's future speed and stability on the water. With the frame reinforced, work shifted to horizontal bracing. Massive solid timber deck beams were brought in, laid across the hull to bridge the two sides. These beams do more than provide a floor for the deck. They add immense rigidity to the entire structure, preventing deformation during the rest of the construction. Following this, the first planks were laid along the upper edge of the hull, marking the transition from framing to planking. Although few in number, these planks signaled a major change. The ship began to have a surface and volume, moving beyond a mere empty cage. By February 2012, the appearance of the Greyhound had transformed significantly. The hull planking nearly enclosed the lower section, extending down toward the keel. The gaps between the ribs vanished, replaced by a seamless and sturdy structural mass. The video concludes with the Greyhound ready for the next stages of finishing. This is more than just building a boat. It is a vital act of preserving and passing down the raw machine of traditional wooden shipbuilding. If the Greyhound grows from a predefined frame, this journey begins within the untouched trunks of the forest. The first hammer strike rings out, deep and solid, opening a small fissure in the log. From there, wooden wedges are driven deeper, bit by bit, forcing the massive timber to split naturally along its grain. Once the trunk is halved, they continue wedging to subdivide the wood into fan-shaped rough planks. Splitting longitudinally along the grain, in this manner, ensures maximum strength and flexibility for the ship's strakes, a structural integrity that modern machine sawing, which cuts across fibers, can rarely achieve. The shaping phase begins. The shipwright uses specialized broadaxes to hew away the bark and excess sapwood. Every precise strike transforms the rugged mass into thinner planks, meticulously chasing the desired silhouette. Once the basic form is established, the surfaces are manually planed. This stage removes the rough axe marks, creating the necessary flatness for the planks to sit flush against the ship's ribs. With the wood prepared, the first protective layer is applied, thick, pungent black tar. This resin not only waterproofs the timber, but shields it from the unforgiving salt and rot of the maritime environment. However, for the ship to be truly watertight, coating alone is not enough. The narrow gaps between planks are filled with wool or jute fibers saturated in tar. The artisan uses brute force to drive them into every crevice with a caulking iron, ensuring a meticulous seal. The planks are now hoisted onto the hull to begin the assembly. Initially, they are held in place with clamps and wedges, a dry fit, to test their position before permanent fastening. Then, each hole is bored by hand, and connections are forged using iron rivets or wooden tree nails. Every joint is a marriage of force and precision, ensuring the planks don't just sit together, they function as a single unified body. The defining characteristic lies in the clinker, or lapstrake method, where the planks overlap. This structure grants the hull immense strength while providing the give and flexibility required to adapt to the rhythmic torsion of ocean waves. And now, let's move to our final story, where the vessel begins not with planks, but with its core skeletal structure. On the massive timber, the shipwright planes and grooves the wood, step by step defining a structure that is both powerful and precise. A team of artisans and engineers works in concert, constantly inspecting and adjusting. Managing a timber of this magnitude is, in itself, a formidable challenge for the entire crew. Once the keel is finalized, the process transitions to the framing stage. Vertical templates are installed with absolute uniform spacing. It is here that viewers witness a miraculous transformation. From a solitary horizontal beam, a three-dimensional space begins to emerge. The rib structure represents a crossroads between the rigidity of oak and the flexibility of longitudinal battens. This stage celebrates traditional mortise and tenon joinery. The wood is carved to embrace itself, creating mechanical bonds that don't rely solely on screws. This is the key to a wooden ship's natural elasticity, a structural advantage that steel or composite hulls struggle to replicate perfectly. The phase that demands the most time and provides the most drama is the planking. This is the moment where wood, an inherently rigid material, must learn to yield to the complex compound curves of the hull. Hundreds of C-clamps are deployed, forming a dense but calculated web of tools. Each long strake is maneuvered into position, subjected to the pressure of the clamps, and tamed using heat, steam, to achieve the desired curvature. This process requires extreme patience. Every plank must fit flush against the previous one, without even the slightest gap. The combination of modern epoxy resins and bronze screws creates a hull that is not only completely waterproof, but also capable of withstanding the harsh corrosion of sea salt for decades. After the structural assembly is complete, the process moves into finishing. The wooden surfaces are sanded, treated, and sealed with specialized materials to achieve optimal smoothness and integrity. Simultaneously, interior components begin to be integrated into the hull. The sight of multiple vessels within the same workshop reveals an organized production process, where technical standards are applied consistently and with repeatable precision. In the final stage, every detail undergoes a last inspection, from the joints and surfaces to the exterior protective coatings. At this point, The ship is no longer a collection of disjointed parts, but a unified whole, ready to leave the workshop and embark on its transoceanic journey. This is a quintessential testament to preserving traditional craftsmanship within an industrialized context. So, we have reached the end of a long journey, from the depths of the forest to the factory floor, and from industrial workshops to iconic maritime monuments. Starting with a colossal western red cedar, where every cut demanded absolute precision, we witnessed how humans confront nature, not through sheer force but through skill, experience, and careful calculation. Leaving the forest behind, we moved into the industrial zone, where nature is digitized. At Sierra Pacific Industries, every log is given its own identity, tracked, analyzed, and processed through the lens of science. Here, wood is no longer just a raw material. It is an object of technology. From debarking and sawing to cut optimization, grading, and kiln drying, every step is governed by sensors, algorithms, and modern automation. Yet, even in this highly industrial environment, the human element remains at the core. The keen eyes of skilled graders and decisions forged by years of experience remain the final factors that define the value of every board. But the journey didn't stop there. When wood leaves the factory, it is more than just a product. It becomes the raw material